Okay, looks like we're live. So, stoichiometry. This it's a problem for some people. Stoikos means item or element. These are both from Greek. Metros means measurement. So stoichiometry means measuring things. So in chemistry, it's how much stuff does it take to make another stuff, or vice versa. Okay. So, say you have 11 wheels, 4 frames, 7 handlebars, and 5 gear systems. How many bikes can you build? Well, you know that every bike needs 2 wheels, it needs 1 frame, it needs 1 set of handlebars, and 1 gear system. So that means you could build, at most, 4 bikes. You would have a few wheels left over, you'd have some handlebars left over, and a gear system left over, but you could have 4 bikes. That's stoichiometry. Okay. Chemistry does the exact same thing, but with uncountable billions of parts, aka molecules and atoms. So we have to be a little bit more precise about what we're doing. Okay. So remember, all roads lead to mole. This is why we do this. So 2 molecules of hydrogen plus 1 molecule of oxygen means 2 molecules of water. Or 2 moles of hydrogen and 1 mole of oxygen to make 2 moles of water. Or 1 gram of hydrogen plus 8 grams of oxygen makes 9 grams of water. So that's why we have to work in moles, okay? Because moles have that same relationship, okay? That's something that you just can't get with mass. So how do we do stoichiometry? If you have 2.5 grams of hydrogen, how many grams of oxygen do you need? And how much water can you produce? Stoichiometry says, okay, we have to convert to moles, and then we relate them to one another using stoichiometry. Okay? So we convert from mass of hydrogen to moles of hydrogen, and then from moles of hydrogen to moles of oxygen. And we do that using the balanced chemical reaction. So, okay, I will go ahead and write it out by hand in this case because you're going to need to see that. So we have, here's our balanced reaction. I'll go ahead and write that back down. Oops. All right, so we have 2.500 grams of hydrogen. First thing we do is we convert that to moles. We divide by the molar mass, which is 2.016 grams per mole. Bring up my calculator. 2.500 divided by 2.016 gives us 1.240 moles of hydrogen. So that should be familiar to you by now. You should recognize how to get from mass of hydrogen to moles of hydrogen using molar mass. The next step is a little different. What is the conversion factor that takes us from hydrogen to oxygen? It's this right here. The balanced chemical reaction tells us that for every 2 moles of hydrogen we consume, we're going to consume 1 mole of oxygen. Okay. So if you started with 2 moles of hydrogen, you're going to need 1 mole of oxygen. If you start with 4 moles of hydrogen, you're going to need 2 moles of oxygen. If you start with half a mole of hydrogen, you're going to need a quarter mole of oxygen. Okay? So that is the stoichiometric conversion. Okay? We just take the numbers right out of the balanced chemical equation. Okay? So where you're going to goes on top. We're going to consume 1 mole of oxygen for every 2 moles of hydrogen we consume. Okay. So the 2 comes right there, and the 1 is right there. Remember, it's an invisible 1, but it's still there. So that means that if we consume 1.240 moles of hydrogen, we are also going to consume 0.6200 moles of oxygen. But I didn't ask for moles of oxygen, I asked for grams. Okay? So we'll convert back to grams. So 0.6200 moles of oxygen multiply it by the molar mass, 31.998 grams per mole. Back to this guy, divided by 2 times 31.998 means that we will also consume 19.84 grams of oxygen. Right. So this was the stoichiometry step, okay? Converting from moles of one substance to moles of another substance using the balanced chemical reaction as your guide. Okay. So the other thing I also asked was, how much water can you produce? Okay, so it's the exact same thing. Okay, so once again, 1.240 moles of hydrogen. Where we're going to goes on top. We will produce 2 moles of water for every 2 moles of hydrogen we consume. So this should be no surprise whatsoever. Okay. But it's 2 and 2. It doesn't matter what side of the equation it's on. Okay, it's not going to really change how we do this sort of math. Just wherever you're going to is going on top. Where you're coming from is going on the bottom. So for every 1.240 moles of hydrogen we consume, we will produce 1.240 moles of water. And once again, I asked for mass. So in this case, it's going to be, I'm not even going to do the multiplication. You don't have to do the multiplication. It turns out it's much easier than that. It is 21.34 grams of water. How did I do that? Well, I could have done the multiplication, even though I didn't. The molar mass of water is 18.02. We multiply that by 1.24, and we get... Did I do my math? I did do my math wrong. You can see, yeah, 22.34, not 21.34. But all I did was I added 2.5 grams of hydrogen to 19.84 grams of oxygen. Remember, conservation of mass. Whatever you start with, you have to end with. Whatever you end with, you have to start with. If we have, a nice balanced amount of hydrogen and oxygen, then all of that mass has to be converted into water. And 2.5 plus 19.84 is 22.34. I forgot to carry the 1. All right, so that's the math that we're looking at here. 2.5 grams of hydrogen. We convert that to moles, we get 1.24. Then we convert that to moles of oxygen. Where you're going to goes on top. So that gets us the 0.62 grams or moles of oxygen, which you convert that back to mass, you get 19.84. And then we can do that exact same math. You don't have to add, but 2.5 grams of hydrogen is 1.240 moles of hydrogen. And then for every 2 moles of water we produce is going to consume 2 moles of hydrogen. So 1.24 moles of water will be produced. And then 1.240 times 18.015 gets the same 22.34. And there's the stoichiometry step, where we use the coefficients from the balanced reaction to relate the 2 substances to one another. It doesn't matter if you're talking about 2 reactants or 2 products or a reactant on a product or even a product and a reactant. It doesn't matter which direction you're going. Where you're going to goes on top. The information you already have will go on the bottom. All right. And there is the note about the conservation of matter. 2.5 grams of hydrogen plus 19.84 grams of oxygen is what gives us 22.34 grams of water. That'll only work for something simple like this, where you have just the one product. If you have multiple products, you will give, then the total mass will still be the same, but it will be divided up among the various multiple products. All right. So, generally speaking, you will start with some quantity of some substance. It could be a reactant, could be a product, it doesn't matter. You will then convert from whatever quantity you're given to moles. Then you do your stoichiometry to convert to the moles of the other substance you asked about. And where you're going to goes on top, where you're coming from goes on bottom. And then you convert from moles back to some other quantity. Okay? Because typically we don't stop at moles just because moles is not what we work with in the lab. So you might have, some volume of a liquid that you're working with. You convert to moles, you do your stoich, then you convert back to, this could be a mass of a solid that you're going to then react with that liquid, or it could be a volume of another liquid. It could be any number of things. This is the stoichiometric step, converting from moles of one substance to moles of another substance. Okay? This other stuff is getting us to the stoichiometry, converting it to moles, converting it out of moles. All right, this example is not going to be on the board, but it will be on the page. How many grams of liquid iron can you produce from 10 grams of iron 3 oxide using the thermite reaction? So I'm going to go ahead and write that down on this piece of paper. Let's bring it back up. All right. So the thermite reaction, that's a fun one. You react rust with powdered aluminum to produce aluminum oxide and molten iron. Okay. It's a very, very, very exothermic reaction. All right, so now we go ahead and we balance this 2 and 2. Okay, so if we start with 10 grams of iron oxide, how many grams of liquid iron will we be able to produce? So, first we convert to moles. The molar mass of rust, let me bring up the calculator, 55.845 times 2 plus 15.999 times 3. The molar mass of iron is 159.687, so we're dividing by 159.687 grams per mole. Meaning that we have 0.06262, need one more, 2 moles of rust. Now, a lot of people get it sort of twisted. They try to take into account the fact that there are 2 atoms here and 1 atom there. Don't do that. Just go ahead and trust your coefficients. They will get you where you need to go. Okay. So now let's go ahead and do our stoichiometry. We have moles of rust. We convert using stoichiometry. We will produce 2 moles of liquid iron for every 1 mole of solid rust we consume. Okay. So you see the fact that there are 2 atoms in here and 1 atom there, that's already been taken care of by balancing the reaction. You don't need to do anything else to take that into account. Okay. You're just going to produce 2 moles of iron for every 1 mole of iron oxide because of the atoms and the way they're working. So we just come back here and we multiply this number by 2, which means that we're going to produce 0.12524 moles of iron. Okay. And now we can convert that back into mass. 0.12524 moles of iron times 55.845 grams per mole. Just remember, this is iron, not iron 3 oxide, so different molar mass. Meaning we will produce a little bit less than 7 grams of iron. All right, so that is yet another example of a stoichiometry problem. Convert from grams to moles. Then stoichiometry takes you from moles of one substance to moles of another substance. And then I convert it back to mass. All right. Now here's an example for you to work through. So go ahead and pause the video and balance this equation, and then do the stoichiometry problem. How many grams of potassium chlorate will you need to fully react with 12.5 grams of sucrose? Did you pause it? I don't think you paused it. Okay, well, welcome back anyway. So here is the balanced reaction. You're going to need 8 moles of potassium chlorate for every 1 mole of sucrose. Yeah, those numbers are big, but that's because you have so many atoms of carbon, hydrogen, and oxygen inside of sucrose. That's all. All right, so 12.5 grams of sucrose. The molar mass of sucrose is 342.295 grams per mole, meaning that 12.5 grams is only 0.036518 moles of sucrose. Now we do our stoichiometry step. Okay, for every 1 mole of sucrose, we are going to need 8 moles of potassium chlorate. So we multiply by 8, divide by 1. And that means that we're going to need 0.29214 moles of potassium chlorate. But I didn't ask for moles, I asked for grams. So we need the molar mass of potassium chlorate. That's 122.548 grams per mole. So 0.29214 moles of potassium chlorate multiplied by the molar mass, 122.548, means that we need 35.802 grams of potassium chlorate. So you cannot really get, when it comes to mass, when you're just dealing with grams, there's no good way to just rule of thumb it, right? Because you see 12.5 grams of sucrose as 35.802 grams of potassium chlorate. Just looking at this, there's no way to see that there's almost a 3-to-1 rate. No, there's nothing like that. You have to go through moles. Otherwise, it just won't work. Okay, that dog ain't gonna hunt. You need to go through moles. All right. So those are all examples of stoichiometry. Stoichiometry is difficult. It is not intuitive. You are going to need to practice. This requires you to be able to convert between grams and moles. It also requires you to be able to balance chemical reactions, and it requires you to be able to read the numbers that you've written down. So work on your penmanship as well, especially you, Emery. God. All right, so that is it for this video, and that is it for this set of slides. I will see you